towards the west, towards the border with Holland and also Belgium. And we are mainly working on the electromagnetic induction to characterize the shallow subsurface up to 10 meters, and also the GPR and also combinations of GPR and EMI. Later on, Christian will tell more about the shallow EMI measurements, calibration and inversion, and we'll focus on what we do with GPR. So it's really very high frequencies that we are using. And it's really the upper spectrum of the electromagnetic waves. And what our kind of approaches are is to understand most what the ground penetrating radar data is showing us. And if you look at some kind of wave characteristics, then it is very easy to get the first arrival time and also the first cycle amplitude that you can pick, and you can get some rough estimate of the velocities. If you have measurements carried out in boreholes, then things are getting more complicated, and you see a lot of wave trains that you cannot really directly understand, but you can still pick the first arrival or the first cycle amplitude. And what we have actually also implemented and also improved is the waveform inversion of the GPR data. So we are using the full waveform, and we also use there a detailed forward modeling tool. FDTD is what we use, and we try to explain everything that we see in this kind of data. So this is actually done very often for seismic data. They have been working on this already for about, I would say, 20 years. And for GPR, we are now also working for about, I would say, 8-9 years to also improve this. And I will show some case topics that we have worked on and try to explain also what are the important aspects to take into account with these approaches. So GPR can be used off ground, in air. The coupling of the antennas is then always the same. And here we have also investigated the concrete layering and also the water content and chloride content in these concrete slabs over here. And because the antenna is in air, we can also estimate a wavelet that the system is emitting. So this is one of the important issues, to estimate a wavelet that the GPR is emitting. We don't know what is emitting because these are commercial kind of systems. And looking at real data, we need to really try to figure out, okay, what is this commercial antenna using for wavelet? And that is what we need to estimate also here. This was using a horizontally layered model approach, and we also did not use a gradient inversion approach, but more a global local search approach, because our number of unknowns were limited. And this way we could also characterize the concrete in this case. We have now recently being more versatile, and we have now implemented also a similar approach where we look at the 3D modeling tool to also investigate the cylinder of the radius of cylinders that are present in the subsurface. Some ray-based approaches, they claim that one can also estimate these radius, but it is tricky because if you pick your arrival times, then you have also errors, and actually the reliability of these kind of methods is not that good. And we have also now implemented a full waveform approach to estimate this kind of properties, and this has been recently implemented by Liu et al. And this is now also being practical for other topics where you want to have a characterization in the subsurface of a certain scatterer, and you have a certain parameterization of the scatterer, and you want to match your measured data with the synthetic data by optimizing these parameters. So this is now also being flexible for other approaches. Then we have also implemented a full waveform inversion for on-ground GPR, also using horizontally layers. We see here also some kind of a waveguide data set. So people that have worked with seismic data, they would see the similarity with the Rayleigh and Love waves characteristics, where you see that there's not only one arrival, but it's really a shingling of different arrivals. Also with GPR, we have this when we have a precipitation event, and this is also then being inverted with the full waveform to characterize the subsurface, and we can then have much more information of the data. and also the subsurface. Usually the GPR data is being inverted for velocities, but now we can also invert for the electrical conductivities, which is then actually also very interesting to compare with also the EMI electrical conductivity or also the SIP electrical conductivities, and then look at the whole spectrum, what can we see and learn from this kind of data. So that is something that we have investigated. And one of the topics where we have been very active is the cross-hole full waveform inversion. We have now looked at 3 different aquifers that we have investigated, and actually the main work has been done by Anja Klotja. And this is actually a borehole setup where GPR measurements have been carried out in between 2 boreholes. And I will show you now one example of what we have looked at. And actually this is a kind of 3D view of part of the aquifer, where we have done a ray-based inversion. And in the past also there was a tracer experiment carried out by Andreas Kemna and others, and there was a plume splitting being observed due to a positive and a negative trace. So you see here these 2 plumes being splitted. And looking at the ray-based inversion results, we see that the clustering does not really indicate certain structures in the subsurface, why this kind of trace splitting was occurring. Looking at the GPR full waveform inversion results, we see that here this kind of layering is indicating the different pathways, why this kind of plume splitting was occurring at this kind of aquifer. So that is indicating the high resolution that we can obtain with full waveform inversion if we use all the data that is available. And to also indicate how this kind of data looks like. So this is actually measured data. That's an example of measured data. We see here a lot of details present in this data where amplitudes are changing very much. And if we try to invert this data by only using the first arrival, then we see that we match the first arrival, but the amplitudes and also the information content here is different than what we have measured. But if we now use the full waveform, then we can actually have modeled data that is explaining the measured data very well. You see here also the high amplitudes that are matching very well, and also over here. And this model is then explaining best the kind of measured data. And here you see also these kind of high amplitudes that are present in the data. And this is actually where the data is being trapped within the waveguide. And to explain this a bit more in detail, I have also indicated here this kind of inversion result that we had from using the full waveform inversion. And we see here we have a very low velocity layer. And if you now look at how this kind of wave is propagating, if we have a source over here in this low velocity medium, then we see that a lot of energy is being trapped within this layer. And this is actually also what we can observe in the data. So that's actually this kind of waveguide is trapping the energy. It's very high amplitudes and also multiple reflections. And if we go back to this slide, you see also these kind of multiple reflections. And actually this is where the source was actually in this kind of waveguide. So that's indicating that with this full waveform inversion approach, we can really explain a lot of what is present in this GPR data. And
so if you went to the previous slide, so let's look at T1.
T1,
yeah.
Yes.
All the coda that's there, is that all? Is that just basically your, a complicated wavelet, or you've got something else that's going on? I mean, how many sort of cycles do you have in just what you consider your primary wavelet?
Well, this is already the question. What is the primary wavelet? And we actually don't know. So what we do to get some kind of estimate of the wavelet that is emitted by the GPR system, we use a start model with also ray-based inversions, and we do a forward modeling, and then we actually deconvolve the Green's function that we get from the forward modeling out of the data. And this is giving us an effective wavelet. So it's an overdetermined system, and we can get a wavelet out of this data such that it is representing best the emitted wavelet, and that's what we use for the full waveform inversion. So this is a very big challenge for real data because we never know what the system is emitting. And for cross-hole data, we assume that the coupling is always the same because the antenna is in the water. But as soon as you put it on the surface, you have to also invert for the wavelet at every position separately. So this is the tricky thing here.
But still, if you look at the coda, it's coming in at 100 nanoseconds. So you've got two positive beats, 3 negative. Is that likely that's just one wavelet that's going down, or is there something?
So actually, we have estimated the wavelet, and it's very often looking very similar. It's a bit broader than the Mexican head. So it has 2 positive and 1 negative, and then some small peaks on the side. Yeah. So this is probably also, if as you look carefully, you see that we do not match this kind of wavelet very well over here. This is probably also because the borehole is very close to the water table, and there are probably don't have enough rays to constrain the data and also the inversion very much. So that is also something, but we should more focus on the intermediate kind of source locations, because there we have a lot of crossing rays that constrain the inversion best. So there are much more details that we have to take care of when we do this inversion, like the start model. If we are too far away from the start model, more than half a wavelength, then we can get stuck in a local minima, and that is also not helpful. You mentioned this morning also the possibility to invert also frequency domain. That is also what we have looked at, to look at frequency domain inversions and also time domain inversions. This is all time domain inversion. With the FDTD, one can also use the FDFD, which, it's tricky because which kind of frequencies do you choose? And there are many strategies that are possible, but you are opening up a lot of more decisions to be made. And I'm not sure if that's the same for also the things that you have discussed this morning, but so for real data, we are still working with the time domain kind of inversion. Yeah. So that was actually, I think, this is the final slide as far as I remember. So here you see that we have the measured data. We get this kind of structure from this measured data, and if we then look at how we can forward model the data, then we can see that we have a very nice match of what we have measured and what we have modeled, such that we can also get an idea of how reliable this kind of inversion results are. We have also talked about uncertainty during lunch. There are also people that are asking, yes, but how certain are you now about these structures? And we could also investigate this, but you need a lot of computation power to investigate this. But I do think in future this will also be something to be investigated. Yeah. So here you see some amplitude spectra that you can also kind of use for estimating where are these kind of waveguides there, and this was actually a preferential flow path in a gravel aquifer that was identified using these approaches. Yeah. So that was in very short what we are doing in the research center regarding GPR and many other projects going on, but this is just to get a flavor of what is our kind of main research topic.
You also mentioned you're inverting jointly or simultaneously both for connectivity and you want to elaborate a bit on that, or any kind of references?
Yeah, so that is actually also in seismics. It's a bit difficult. They are looking at attenuation and velocities, and we from Maxwell's equations and also the full waveform inversion approaches that you can derive, we can directly also define gradients for the permittivity and the conductivity at the same time. There have been different approaches, first update the permittivity and then the conductivity, and we have found out several years ago that one can also update the permittivity and the conductivity at every iteration step, and that this is the most stable one to finalize and obtain the best results. Yeah, so that is something what we have been looking at and also investigating a lot, and we can say that this is the best approach to use for real data until now. Yeah. So what we also look at is remaining gradients. So for every iteration, we get gradients, and we can also look at how many gradients are still remaining, whether we still need to update this, or whether we see that all the kind of misfits are smoothed out of the whole domain, or whether one area is having a lot of misfits regarding the gradients. But this is also, there are many aspects to figure out at which iteration should I stop when the RMS is not changing that much anymore. But there are many other aspects that we can investigate. So that is still, continuing currently. Yeah. So we are also now trying to go from a 2D FDTD model towards a 3D FDTD model by also incorporating the borehole itself and also its filling, because there are many aspects that also, the borehole is influencing the data and the measurements, and that is also how we try to get the reality as best represented in the inversion as possible. Yeah. So thank you.
Thanks.
Just 1 second, I'm just going to get your screen shared. And if you'd like, you can use this and then back and forth to change your slides.
Yeah. Then go maybe to. Cannot go back. Okay. Okay, so hello, my name is Chris van Hebel, and I work in a, so to say, bigger group where we investigate and study and use and also develop fixed boom electromagnetic induction systems. So in the group, we start like in the very small scale. For example, we investigate on the point scale. We use EMI data together with soil cores and to study, for example, the reducing of fertilization of fertilizer, for example, in this project here. Or also we're investigating the weathering zone in the project of Igor Dalbo, and I also wrote his name on the other version here. But yeah. And we also look at geomorphological changes in the project of Cosimo. But and I'm mostly interested in the calibration and also in the quantitative inversion then of this fixed boom electromagnetic EM induction data. So what do I mean with fixed boom multi-coil EMI data? So when I talk about this, I mean instruments that we place in sleds, so they have relatively short offsets between the transmitter and several receiver coils. So we do have a system that is 1.20 meters long. This has 3 receiver coils. It's a CMD Mini Explorer. We do have a system that is a custom-made special edition of this Mini Explorer that's 1.80 meters long and has 6 receiving coils. We can orient them in VCP or in HCP, so with vertical coplanar loops or horizontal coplanar loops. And we also do have a dual EM. This has 6 coils, which measures simultaneously with perpendicular oriented coils and horizontal coplanar loops. So on the next slide, this looks a little bit busy, but I shortly explain the calibration that we do. So we measure with our multi-coil system either along a relatively short transect, so we record EMI data, and we co-locate either electrical resistivity tomography measurements on the same transect, vertical electrical soundings. Then at a test site that basically should represent the whole ECA range from super low to super large of this particular test site that we're currently investigating. So what we use is from the inverted ERT or the inverted vertical electrical sounding data, we use the electrical conductivity distribution that we have at this particular spot. And we use a Maxwell-based exact EMI forward model together with the EMI instrument specification, so the specific frequency of the used instrument, the specific coil orientation, and also the offset or the separation between the transmitter and the receiver coil. So this is then inserted in our EMI forward model, and we are able to predict apparent electrical conductivity, so the quantity or the value that the EMI instrument actually measures. And we then perform a linear regression between the measured and the predicted values, as shown here, to get calibration parameters, so coil-specific calibration parameters. So each coil of this instrument does get then a specific scale factor as well as a shift, so the outcome of a linear regression, which then delivers us quantitative EMI data or ECA values. So of course you may ask, why do we do all this? Why do we do the step with the calibration? This is the second slide. So we see here on top, this is a 120 meter long transect. This one is a shorter 30 meter long transect. We see here in the middle panel always the inversion of uncalibrated, so simply just measured EMI data. Here we measured the EMI data with the EM38, single offset EM38 in VCP and HCP, and with the profiler. And in this more recent study, we used this multi-coil EMI system, the CMD Mini Explorer, where we measured also in VCP and HCP with these 3 different coil offsets. And yeah, as I said, in the middle panel you see the inversion of uncalibrated data, which does of course not match at all the reference structure that we obtained from ERT. And after calibration, we see that here this is a two-layer inversion. We see that the structures where match or resemble also the ERT inversion. And also here we see that the subsurface image that we get out from quantitative or calibrated EMI data inversion pretty much also resembles the structural information that we get from ERT. So now, of course, you may ask, when we just do something along a transect, why do we measure with EMI and then calibrate the EMI data with ERT? But we are not interested in transects, so we are interested more like in the large scale applications. So because of course, so this 30 meter ERT line, for example, takes like assembling, deassembling, and measuring like 3 hours, I would say. And we can, of course, measure much larger areas with EMI in 3 hours. So that's the basic idea. So we do not invert like transect data with EMI, but large scale data. And this is also then shown on here. So we see here the subsurface structural information from 2 different test sites. Over here, or maybe I first explain this middle figure. So we see here the soil here in this middle part of this middle figure is basically very gravelly. So we have a very high gravel content over there, except of buried paleo river channels. So river channels from an ancient river that are covered. I was yesterday at a more public presentation, and there I learned that the term paleo river channel is not really known, so that's why Shorty said that it's a buried river system that is actually not present at the surface anymore. And then towards the east, we do have a very drastic change in the soil. So we have a very fine textured soil toward the east. It has a very high loam, silt, clay content. And that's actually what we also see. So this field here, I call it upper terrace, the gravelly upper terrace, and LT lower terrace, like a transition field, upper terrace, lower terrace transition field. And we see in the inversion results that here, exactly on this border, we do have a massive gravelly layer here, which is reflected in greenish colors that stay for very low electrical conductivities, layer electrical conductivities, and the electrical conductivity is increasing towards the west. This layer also, or this field also here is managed as a bare soil field. That's also what we see on the cover, on the top, so to say. So we do not see it in apparent electrical conductivity measurements but directly, but the inversion result nicely shows us that we do have like a homogeneous bare soil top coverage. This field here in the central part that is characterized by this buried Pali River channel does has an east-west directed channel that actually goes over in this field here, and a north-south directed channel. And we also see very nicely from the inversion results that the channel, that's the east-west channel over here and this north-south channel over here, it appears at approximately 0.75 meters depth. So we have a pretty much homogeneous plowing layer. So these are all agricultural fields. So we have a plowing layer of about 30 centimeter depth, and then another layer, and then these Pali River channel structures do appear. So we also validated these, I call it quasi-3D, large-scale quasi-3D EMI inversions. So when we start with at these transition field, we see from older ERT surveys or campaigns that has been done there. That's also again a 120 meter long line here, which basically was recorded from here to here. So starting in this gravelly zone and ending here. And we see that the structures match very nice, which is also the case for even an older ERT inversion in 2009, which was running from here to here. And we see that here we basically have a 3-layer earth, which was also found by the quasi-3D EMI inversion. And then we have this homogeneous structure here, which was also found, and another, another 2-layer earth at this location here. And also the other structures match very well. One direct application for this, when we go again to this Pali River channel field, so which is actually a cropped field, we made some cross correlations with some properties, and one property, for example, is a leaf area index. So that's the leaf area Earth, and we see that it's not, in this particular case here, it's not the plowing layer that is responsible for crop performance, but it's actually the deep buried Pali River channel that delivers water and also nutrients to the crops, such that they show up with the large leaf area index above these Pali River channels, and they are like thirsty or almost witting beside this Pali River channels. Yeah, so with this I also want to shortly acknowledge different projects that were involved, and also like to show you the references that were shown in the presentation. Yeah. Good, thank you.
Can you tell me what a shuffle complex evolution procedure is?
Yeah, so basically you can think of, it's like an evolution system. So during the inversion, so to say, like it's like evolution. Huh? So better parents, they also call it parents then in the description, are preferred to produce offspring, and the worse of parents are, so to say, discarded. So the inversion code starts to sampling randomly from the search space, and then is comparing, or let's say all the population that is sampled is then put in different complexes or subpopulations, and then each population is evolved independently. And then at some time periods, so it's shuffled throughout the complexes, while the parameter sets that do produce a minimum misfit or a smaller misfit are preferred, while those parameters or parameter sets that do produce a larger misfit are discarded. And then at certain search steps, also new, so to say, parents or parameters are sampled from the search space. So that's basically how the inversion works. Yeah.
And how many parameters do you have?
Yeah, that's a 3-layer inversion here. So we do have 5 parameters. That's the 3 electrical conductivities and the 2-layer thicknesses. And we measure at least, so always in this study here with the Mini Explorer and VCP and HCP with the 3 coil offsets. So we have 6 measurements then, and these 5 parameters to invert for. And we, yeah, as shown in the very beginning, so this was in the beginning, and now we also extended the instrument, or yeah, we have much more instrument in stock, so to say. That's kind of our basic procedure, is to measure with the Mini Explorer and also with the custom-made special edition in one go, and from time to time also with the dual AM, and that's basically the chain that is then also pulled by the quad or behind the quad to, yeah, discover or to explore relatively large areas. Yeah. Mm-hmm. There's another question.
You just explained the calibration and stuff, but how do you know in advance the range of the expected positivities if you don't know the subsurface?
Yeah, it's like, it's a very practical question. So we start in the field and we measure the complete field. And then we download the data in the field, we plot them, and then we see how the conductivity, apparent electrical conductivity range of this field is then of this test site. Yeah. Okay.
Thank you.
Thanks.
So any volunteers to go next? Sure, come on up. Which one's yours? Overview. Perfect. Oh yeah, sure, no worries. The important guy. Fair enough. Fair enough. Well, there's actually 2 things I want to bring up. There was a form that went around. Yeah, I was hoping everybody, if you've come today, if you can make sure that your name and email are on there. I will follow up with a few resources, like the links from the video today, as well as some links to where the slides can be downloaded and things like that. I'll upload the slides that Doug showed this morning, also to the website. They're not there right now, but by tomorrow they should be. And then another thing that we've started, and this will also come around in the email, and we started this in Australia. It was something that came up in conversations during Disc Lab Day. It's an EM wish list. And so the idea behind it is we just have basically created an open forum for people to submit ideas on things that would be nice to do with EM. Like, wouldn't it be nice if EM could, or applications that you want to try, resources that you think would be beneficial. And so it's really just meant to be like a space for collecting ideas and things like that, especially in the spirit of open source and collaborating on ideas. And collaborating on software and on tools. We're hoping to sort of just draw on some of these ideas and potentially connect you with some people who are maybe interested in similar things. So that'll come through as a link. It's very open-ended, and so we'd love to get your ideas. And you can also see on there what other people around the world have been up to. So, which is kind of cool. The other resource I'll show you real quick while we're waiting for Doug is on the website, we've also started a blog. And we've been trying to keep somewhat updated. So it's always going to be lagging behind a little bit because we're trying to write as we're, delivering the next course. But these are all blogs about previous locations we've been at. And on there will include a bit of an overview of the day. For each one, we've done a write-up on like a specific section. So it's sort of like a synopsis, a little overview that might be kind of interesting for you. And then the one thing that, for us, or for me at least, has been one of the most valuable resources that we have is actually the summary of the Disc Lab Day. So with this, we've been putting everybody's slides up there. So if there are any of you who would prefer not to have your slides uploaded, please just come let me know and I won't upload them. But if you're willing, then they'll be up there with your name and a short description of what you've done. And so it's kind of cool. Sorry? We can do either. I'll probably put, if you'd prefer to have it uploaded as a PowerPoint, I'll also just include a PDF because some people, like if they're on Linux, have trouble opening them. But yeah, either or. Yep, no problem. Yeah, so it's kind of interesting to actually be able to go and have a look and see what problems people are discussing and working on worldwide. So that's been one way we're trying to collect all of this. And so in order to actually get to the blog, I'm sure, did you see, hopefully most of you saw this site, disc2017.geosci.xyz. So there's a link to the blog here. It's also in the navigation. And then all of the material for the presentations is going to be here. And I'll append those other presentations that were given this morning. The other site to show you is GeoSci.xyz. So Doug mentioned this briefly yesterday. And what this is right now it's meant to be a portal to some of the open source resources that we've been working on and that are absolutely open for contribution. So the GPG is a resource that was started a number of years ago, and we've recently upgraded it to be sort of more modern on the web. But it's for basically introductory geophysics. So we use this for an undergraduate geophysics course that's primarily given to non-geophysicists. So they're mostly engineers and geology students. And it's really a once-over of all the geophysical methods. And so there's a couple courses that are using it. We've been using it at UBC, and there's now a university in California that they've adopted it for one of their courses.
Can you contribute?
Yes, absolutely.
Can you branch it?
So if you have content that you would like to add, yeah, so the best thing to do would be to first get in touch, and then we can help figure out where it should go. But it is all up on GitHub. You can edit any of the pages. So there's been people, typo fixes are always welcome. But if there's a page that you'd like to add, yeah, just get in touch and we can make that happen. And that's the same thing with EM GeoSci. Same idea here is that it's all completely editable. Case histories are most welcome. For those, what we suggest is you first get in touch because it is a little bigger, and then we'll help structure and get all that on. And then once it's up, you can edit it.
I guess you make slides.
Yes. There aren't slides up here yet, but that's something that we'd be working on in the future, is trying to tie like all of the content that's been produced together a little further. Yeah. Sounds good. Perfect. Well, we can do a little more of a tour after that. But now Doug's back. No worries. So if you want this, the slides will go forward and back, or you can use the computer, whatever you prefer.
Sure.
Oh, maybe it's not working.
No, just pointing stuff. That's okay. I'll use the computer then. Don't worry. Okay, hi everyone. So my name is Frederick Nguyen. I'm currently the head of the GeoCube division, which actually is in the Faculty of Engineering at the University of Liège. And GeoCube basically stands for, it's a research division. I think we're about, I'm guessing probably something like 30 to 40 people, and we work on hydrogeology and environmental geology problems. That's one group. Applied geophysics, that's another group, that's our group, and geomechanic, and or geotechnology, as they call themselves, geomechanics and engineering geology. So we are not so much academics. You see that we are like 4 academics, and then the rest is mainly like PhD and a few scientific and engineer as well, to basically also maintain the labs. So we have 3 laboratories, one which is basically soil and rock testing, so that is really geomechanics. We have an analytical chemistry on liquid phases, so that's more related to the hydrogeology, and we started, so I started the group in 2007, so that's our 10-year anniversary actually this year. So we started having a bit of petrophysics in there with now some SIP equipment together with the people from Munich and the Huisman, and also a temperature control system for all the shallow geothermy that we've been also discussing over lunch and over beer. So in terms of infrastructure, we play around at different sites, but we have 3, let's say, permanently equipped sites, which is one is in close to Liège, Argenteau. That's where we did most of our open system geothermal experiments. We have one site on the campus, so that is called Sartillement. So you see here we have 4 deep borehole, which are 100-meter deep, and it's being heavily characterized with imaging and equipped also with fiber optic sensors to do some closed loop system tests. And the final site that is actually a new site that's been finished this year in Commenster, which is even closer to our campus. So basically, as I said before when I introduced myself yesterday, we sort of subdivide our work in 3 main problems. So the first one would be inverse problems in geophysical imaging. So I really sort of did my PhD in that because I worked on geophysical imaging of active faults in Europe. And then I went to with Andreas as a postdoc in Jülich and started working on seawater intrusion. That's what got me into hydrogeophysics. Data simulation approach, because as we work into different process-based methods, you need to try to incorporate different types of data. And then environmental geophysics, that's where I would put it actually, the geothermy or applied geophysics to contaminated sites. So we basically also work at I would say, different scales. So I'm just going to briefly, this is a short talk or presentation, basically those 3 main topics. So one topic that we recently published last year, I guess it was an overdue publication also with Andreas. It's a minimum gradient support inversion, so like focused inversion of a time-lapse tracer. So I don't know if you're familiar with the MGS or minimum gradient support approaches that's been developed by Zdanov, for example. It's try to get, let's say, well, minimalistic image to basically explain the changes that you would observe in your data misfit. So this is basically applied to a tracer test. So it's been done a lot in static characterization to try to find sharp images, someone mentioned just previously. And the goal here is to build up an objective function in the regularization to try to obtain as small features as you can in the image, basically. So we use basically a field test, and we also validated the approach in the synthetic modeling. So this is the field test. So image is pretty dark, but you have a borehole here, which is in a fractured aquifer. It's fractured limestone. So you would normally see here a plain limestone and a fractured limestone here. And we injected for about 4 hours at 15 to 20 meter deep, basically a salt tracer. And we recorded a line. We were supposed to be perpendicular to the flow, about 15 meters away from there. And you see the line is about 200 meters long to make sure we actually captured the tracer. This actually was the work done by my first PhD, Tanguy Robert. We finished in 2012. So if you do a smooth inversion and then do a difference inversion, you will find this. This is the background. So you see here the limestone with high resistivity. and the top layer unconsolidated sediments with lower resistivity values. And you see like a faint image here, which is actually the signature of a salt tracer. You see a percentage changes, so we have about minus 15% changes. But the idea, and so this is what you would get equivalently on a numerical modeling basis. You would get this, because we use smoothness constraint approach, you would get the smoothest blob. So the idea was to try to refocus it. And the good thing when you work with time lapse is normally the objects are a bit more, or that you're trying to reconstruct, are a bit more simple than for static cases, because you have 1 or 2 anomalies. In this particular case, a fractal network. So here we model basically the small focus change of minus 20% is actually the difference here. This is actually the background images that is inverted from this data. Not the data, from the model. And these are basically different inversions. And the letters that you see here basically corresponds to the difference here, variation of one of the controlling parameter of the MGS approach, which is the beta parameter, that basically will focus the images or make it smoother or focused. So you see here, and this we actually, so the idea is try to find an automatic way to actually provide this beta parameter. Like if you look at the literature, there's been different approaches. Some of them are arbitrary, some of them are empirical, but there's not like a unified approach. So our idea was to find actually something that relates to an object, some sort of objecting function. And so we look at basically the time-lapse data misfit and how that will actually, how that will behave with respect to the beta parameter. And you see here that we have a nicely convex shape where the H is actually would be the minimum in terms of data misfit. And if you look at the H between the different images, you can actually see that it's the more compact image. So that sounded like actually a good approach to try to, because this looked like something you could actually search with a linear search approach. So we transpose this approach then to the field, and this is basically again the different letters represent the different results that we get here. And you see that if you go to higher values of beta, then you get really smooth image, quite similar to the smoothness constraint approach. And that for the minimum, I mean, the one that provides the minimum data misfit, we actually managed to get a quite focused image that would position exactly the position of the tracer in this fractured zone. So that is one example of.
What is your vertical axis? Is data RMS?
It's time-lapse data misfit.
Yeah, but what's
that'd be would mean square of the time-lapse data misfit.
Where is the iteration 1?
Sorry.
Oh, I was just looking at the vertical axis, so it's got
Yeah.
data RMS minus iteration 1.
Yeah, at iteration 1, after the first iteration. So we start for the background. It's basically like almost a linear inversion. It's a one step.
Okay.
Yeah,
Okay.
it's a one step. Yeah. Yeah. So this was basically published as a letters in geophysics with this case study. So now we try to also validate it with different types of time-lapse data that we collected on the different fields. Second development that we've been doing is a lot on data assimilation. So we've seen a lot of nicely multiphysical geophysical data that you showed. In this case, actually, basically, it's a different framework. It's more of a process-oriented framework where we try to understand. In this case, it's again heat storage actually in the shallow aquifers. So where we do some heat tracing test or heat storage test that we monitor both with point sensors and distributed sensors and tomographic images. And we basically, this is a flow chart, but basically what we do is first, so we do this in the stochastic framework, and our first idea is basically because we have this huge prior uncertainty, right? And basically our geological type of scenarios that we would consider. So our first job would actually be to start to reduce this prior geological uncertainty using our geophysical data. So that is one work that we've been doing. So that is this probabilistic falsification of basically the geological prior, and we've been using multiple point geostatistic to basically simulate many different geological scenarios and looking basically with the geophysical data collected on the field which one was most probable. So that is the first steps. Then if we want to assimilate different data, the basic idea here is that instead of doing inversion, that is instead of doing using hydrogeological data and hydrogeophysical data to try to find some parameter. And then from the parameters to try to make some prediction. We will try to go directly from the data to the prediction of interest, that it will basically bypass completely the inversion. And so that's why it's called prediction-focused approach. And the idea to do that is that once you have defined your prior, you basically do some forward simulation. In this case, it's basically a heat storage and a heat tracing experiment that we're doing on the site. And then you get different responses. This can be a temperature curve, for example, where response time, or a distribution of temperature in the aquifer that we are able to simulate. At the same time, so this basically contains all the physics of your problems, your boundary condition, your excitation, the geometry of your aquifer, and everything. Then we use some petrophysical relationship and geophysical forward model to basically simulate the data that would be collected on the field. And we get our data, right? It can be time-lapse, it can be static. And then one of the core approaches to do a correlation analysis is canonical correlation analysis, where we'll try to find some linearized relationship between the data and the forecast and the predictions. Because if you manage to get those, so we basically, what the steps are basically to reduce the high dimensionality of the problems by using a principal component analysis approach. And on that basis, we basically then compare the response with the data. If you do find such a correlation, which would be linearized actually, then you can make a Gaussian regression out of it, so define a probability density function, so define a prediction as a function of the data that has been observed, and then to sample that distribution, and then to build up the full posterior distribution of your heat storage or your heat tracing experiments. So basically, this diagram basically completely skips the inversion approach. So we don't try to recover parameter and then to do the prediction. What we try to do is make sure that we get the right physics and that we get also the right observable data, and that we have a link between the two. If you manage to find a link between the two, which actually can be used to design experiments, so that if you manage to get this link, then you are able later on, but then to predict without having to do the inversion. It actually saves a lot of time. And this is actually quite interesting. Unfortunately, it requires quite a lot of forward modeling, which is why it's difficult to use, for example, with GPR at this stage. But actually, it's good because it can also, you can use it to test different hypotheses. So this is one of the great advantages of it. And lastly, this is something that we've been working with Tamara Pilowski, who is a PhD in the group. It's more, the image is not showing up so nicely, but those are actually nice image of electronic microscopes of bacteria aggregation, actually. So you see here, it's one called Bacillus, and then here you have different types of other bacteria. We have different, basically, biomembrane electrical properties. And the idea was that we jumped into that because we started using geophysics as a tool to monitor bioremediations. And we had problems understanding the responses that we get in the field. So the idea was that based on that, we went back into the lab, first at the tank scale, and then at the basically at the column scale. And this is really just suspension scale. So we wanted to decompose basically the SIP signal that we get from first the hydrocarbon themselves, then of the bacteria themselves, and then at a later stage, the bacteria together with the hydrocarbons. But this is just the first stage. So you see here the imagery part of the complex conductivity. So basically here you see a response in one of the bacteria type that you don't see in the other bacteria type, so the one in the green, which is the Bacillus one. And well, you would have to trust me here, but what you would see here in the image is that here you actually have aggregates of bacteria as well as biofilm around it. Actually, it shows nicely on the screen, but you can sort of guess there's a sort of huge mass here. And this is like 20 microns. On the other images, you see that basically the bacteria are all separated. So they're not aggregated. So they're, and those ones basically don't serve the same polarizability as the other one. So this is really ongoing results. And so we hope to understand more basically on the bioremediation of contaminated site by going into a much smaller scale. And I think this was my last slide. Okay, so if you're interested, we get all publication is basically at our institutional websites, and then you have our own website, which where you can see different results. Yep.
So the scale on that, are those, I'm just trying to figure out.
This is microsieverts per centimeter. Yeah, this would actually be a really small phase shift. Like, quite small, like point. I forgot the scale, but it's yeah, it's below the milliradian scale.
Okay.
So it would be barely noticeable on the field actually. But this actually has been so it's a bacterial suspension which has been washed. So basically, we grow the bacteria, and then we basically wash them, and we try to separate them from the medium in which they grow, because if the ionic strength is too strong, basically, it would kill the polarization. And then we resuspend it before measurement. And there is no activity here of the bacteria, so it means also the membrane properties have changed. So now what we try to do is to make an online circuit with the SIP integrated in it, where we could actually change the metabolism of the bacteria directly. A bit like what Maxi showed in the time, to be able to trigger, for example, their activities, which is actually not so trivial to do.
So how actually do you measure these? Do you just put them in a little?
Yeah,
container?
I don't. Yeah, I have a picture of them, not here. So they're in an extremely small container, sample holder, and that is being handled. And then the SIP system is just. So there we have 2 electrodes and 2 plate electrodes on the top. It's a similar type of setup that Andreas showed, except that it's much smaller. But it actually took a lot of time to calibrate it properly, so to get 0 phase response for the water. Also because the signal here is quite small.
And then if you're going to try to put the mechanism for polarization for the bacteria into something that or they're thinking about either electronic or membrane or something else, where's all charges being built up?
Yeah, well, here we think about like we don't know if it's the bacteria themselves or if it's basically around the aggregates. So like an electrical double layer around the aggregates where we have the biofilm that will hold the charge and that will actually polarize us. Yeah, but then it's going to be a different story when we put them into a porous medium. It's going to be more complicated because then you need to make sure that they grow in a porous medium in sort of homogeneous way. So you basically would have to recirculate basically the fluid within it.
Interesting. Yeah. So you said you published sort of some details and examples on your previous inversion methodology.
No.
Where sort of inversion without having actually been doing forward modeling.
No, the formatting is in there, but we don't do the parameter estimation. So so the PFA approach has been published. Actually, is something that was developed by Celine Schneid, also from Stanford, and this is being published in Water Resource Research, I think, for hydrological problems. And now we submitted the manuscript for ERT. For ERT.
So is that online on your publications, or is that?
It should be, yeah, I'm pretty sure. Yeah, the idea was to get, basically it's, we started it because we wanted to have more geologically realistic models and try to plug in some more of this geological information. That's why we started with the multiple point geostatistics, because you could plug in independent information from outcrops and boreholes. Basically, we don't have any, so independent prior, basically. So really geological information.
And what sort of a software or procedure do you have for generating, geologically realistic models?
So that's
that's always a tough challenge, right?
Right. So it's basically okay, correct me if I'm wrong. It's the Tetris. Tetris software allows you to generate the training image. And then you basically specify for a level aquifer, you would specify, for example, the size of the clay lenses, the size of the channels, bars, and you would give like uniform distribution or Gaussian distribution, however you would like. Yeah, our first idea was actually to use the geophysics to define the training image, but because we use the geophysics to falsify the prior information, we basically buy it our own, and we will be running it circles. So we wanted to have one independent information for the prior, and then for the validation falsification approach. Yeah. Okay, thanks.
Who'd like to come next? And then is yours on the USB as well? Okay, perfect. It should be up here then too.
Are you sure, Sven? Do you want to go first?
Oh yeah. Yeah, whoever likes, doesn't matter. Is this one yours? There you go. So just the arrows on the keyboard.
All right, we have the laser maybe?
Yeah, the laser is there.
Okay, so hi everybody. I'm Thomas Kremer. I'm working at the University of Liège, also in Frédéric's team. So I choose to give a very quick presentation about surface nuclear magnetic resonance. It's a very less known and less used method in geophysics, probably I think because it's quite tricky to get very good quality data, and it's also relatively new in developments and all. But I think it deserves to be known because it can give you a very strong, I guess, additional information for solving many different geophysical problems. So what can actually SNMR method do? The main thing is that it can give you direct estimate of the water content in the subsurface, which no other geophysical method can do. It can help you also localize your water, so get the depth and the thickness of your aquifers. You can also distinguish free water from bound water, and also estimate hydraulic properties like porosity or hydraulic conductivity values. So it's pretty useful information. How does it work exactly? The basic principle is that you will try to flip the magnetic moments of hydrogen atoms that compose the water molecule, and then try to measure the precession magnetic field that is created by the return to the initial position. So if I do that step by step, hydrogen atom, they have a spin, a non-zero spin, so they rotate around themselves, and they also have a magnetic moment, small. So they kind of behave like small magnets. And if you place small magnets in a static magnetic field, so in our case, we use the Earth's magnetic field, then they will kind of align in the direction of this field. I say kind of align because, okay, here I have a very dark picture, but they're not really aligned. They're precessing around this axis. But the whole addition of all these magnetic moments gives a magnetization vector that is indeed aligned with the B0 field. So anyway, the idea then is to come and mess with this alignment. How can you do that? You can set up a large wire loop on the ground and produce a very specific electromagnetic field at a very specific frequency that we call the Larmor frequency. And if you do that, you will flip the magnetization vector, the total magnetization vector of the water molecule. And when you cut this pulse, you will have a precession movement of this vector that will slowly come back to its initial position. And this precession movement will produce secondary magnetic fields. And that's what you're aiming for. And that's what will give you the NMR signal that you're looking for. So if we look a bit more closely at this signal, you see it's an exponential decaying sinusoidal form. And we're interested mainly in two parameters, the amplitude, that will give you a direct estimation of the water content, and also the relaxation time of this exponential decay that you will be able to link with the hydraulic properties of the subsurface. So then the idea of the method is to repeat, to measure this kind of signal for several intensity pulse, for several pulses at different depths, and so you will basically make a sounding curve and invert in 1D or maybe 2D if you have the tools to do that, to get a spatially distribution of your water content and of your relaxation times. But one thing is that here, this picture is quite like ideal case. They represented the noise here, which is very small compared to the signal. Unfortunately, this is very rarely the case. In the best cases, we measure amplitudes of the NMR signal of about a few hundred nanovolts, but we almost always, especially in this kind of, if you're close to cities or anywhere where there is a lot of cultural noise, you will have much higher noise levels. So basically, the noise levels, you can identify three main components. Harmonic components, which are mainly due to power line. So you can know quite well how this is done because it's harmonics, right? You have more random events and very high energy events that we call spikes that can happen when you have thunderstorms or electric fences around you. And you also have like uncorrelated noise or white noise that can be due to electronics from your device or to maybe an unknown origin. And so we have specific techniques to deal with each one of these noise. And you also have more global techniques that kind of try to take into account all the noise that you get. One of them is called the adaptive reference noise cancellation. The idea is to put a reference loop between your noise source and your primary loop. And so you will be able, during your measurements, to calculate the transfer function between the two and to subtract an estimate of the noise that is in the primary loop. So this is a very efficient method as long as you have one noise source. And that's where all the difficulties that come, in my opinion, to this technique is that as soon as you get more noise sources, let's say a village somewhere, a windmill, another power line source, then the efficiency of all the methods that we know of, they decrease quite quickly. And so the challenge we face working SNMR methods in areas like close to cities or in agro-urban context, I call them, is to adapt to the context where you have multiple sources of noise that you don't necessarily know very well. And just to give you a very quick example of how we try to adapt to this, in the case of harmonic filtering, one method is based on the construction of a model of harmonics. So you will generate a signal that will try to match as best as you can the harmonic that you're measuring. So you will try to determine the parameters of your model, mainly the amplitude, the phase of your set of harmonics, and also the main frequency, and then subtract this model from your data. This is quite efficient also when you have one noise source. And so here is a quick example. So the image is too dark, but basically we did some measurements around here, and we had a very, very high voltage line here that we identified as a very potential high noise sources. And we had a very small electric line here that at first we didn't know about. And so what we did is naturally to try to do the harmonic-based filtering method. Okay, so let me say that sentence again. Here you have a fast Fourier transform of our signal, what we measured. We can clearly see that the harmonics are dominating the energy of the signal. Every 50 Hertz, we have a large peak. And so we try to apply a classical model-based harmonic to this. It's quite efficient, so we did it between just in this frequency range between 1,000 and 3,000 here in this picture. And so we identified the right frequency. We have a significant reduction of the noise, but we still have some harmonics left. And the reason why is that, in fact, this second electric line also has an impact on the signal we measure. And to improve the noise reduction, we had to make the model-based harmonic filtering considering two fundamental frequencies. So, and then you have an even better noise reduction. But the thing is that when you start doing that, you're building a more complex model. You have a computation cost that increase quite fast. But this is just a very quick and simple example on the lead that we are following. And the fact that it's very important to better understand all your noise source, all your noise environment, because here it's a pretty simple case, only two electric lines. It was in a very remote place in France. But very quickly you can have a windmill over there and a train station there, an airport. I don't know, a plane going over you quite often. And so, yeah, these are the kind of leads we're following to try to improve the use of this method in Western Europe environment where there might be a lot of noise. And so I think it's my last slide also. If you have any question.
Those two frequencies are pretty close.
Sorry?
I said those two frequencies look pretty close.
Yes, they're very close.
I can go to a lot of countries that have a lot more variability than that.
Oh, you mean on the harmonics?
Yeah.
Yeah, probably. Actually, this might not be the most efficient. This model was based on a quite small, how to say that? Mainly we were searching for frequencies between 49.9 and 50.1, which is generally accepted. Harmonics are not supposed to deviate too much from that, but they can, it's true. In some places you have a stronger deviation. And maybe if we do the same search with a higher range, maybe I will find that the optimal frequencies to diminish this noise are different. I'm not saying they are the real harmonics from these two lines, but they gave the best results so far. And so here we don't see it, but maybe we are looking for an NMR signal around here, but even such noise reduction is not enough to see the NMR signal yet. You have a lot of more processing to do to get there. Or there is no water and you don't have a signal to find, which is possible also sometimes.
So on your typical surface NMR survey, then you just run through a spectrum of frequencies, do you, as far as your transmitter?
Excuse me? Yeah.
Maybe it's on your very first slide.
Yeah. Do we go through a range of frequency, you say?
Yeah.
So now the pulse, I think, is quite, I'm not so sure, I think it's quite narrow around the Larmor frequency. The Larmor frequency that will help you flip in the best way your magnetization vector. So you aim for a frequency, but I think if you take a look at the Fourier transform of the pulse, you still have some frequency content around the Larmor frequency. So if you're a bit hitting on the side, you still can excite your protons. Was I answering the question, or maybe not?
And then, sure. What is the frequency of the Larmor frequency?
Well, that depends for water molecules. That depends on which hydrogen you're aiming for. So for water molecules, this is a gyromagnetic ratio. So it's a physical constant, and it depends on the intensity of the magnetic field. So for example, if you're looking for, at the same place, if you're looking for water or hydrocarbons, you won't use the same Larmor frequency if you're not hitting the same hydrogen.
Right.
So But that's one of the challenges also, is to know your Larmor frequency very clearly, so to know very precisely the value of your magnetic field in the area of study, which can also vary at the same time sometimes, so it's not always easy.
And then how do you actually get like a sounding that will tell you something, like what's happening as a function of depth, what's changing?
Right, you're changing the pulse moment. So the pulse moment is mainly you're changing the intensity of the current. You will inject short pulses and then always the same length of pulse, but then you will increase the intensity. And so your sensitivity function is supposed to go deeper, and you will do that for maybe 30 pulses of different intensity.
I see. So the sensitivity function stays the same, it's just that you're changing the amplitude of the input, is that what's happening?
Yeah, so the sensitivity function will depend on the amplitude of your signal. It still has the same form, but if you change your intensity of current, you change your pulse moment, then your sensitivity shapes, they go deeper in the ground.
Yeah.
They are higher and higher at deeper locations.
But you really have just one function that's going all the way down, right?
Yeah, yeah.
And then you're just exciting it with greater amplitude. So at some point down here, if you have a very low amplitude excitation, you know.
Oh yeah,
not
yeah,
sensitive
absolutely,
at all.
absolutely.
But then if you increase that, it's just like the whole amplitude of this function is increasing. So
Yes.
then okay.
You ever build up physically and then every pulse you sound like, I mean, first 10 meters, and the next one, the first 20 meters, the next one,
Yeah.
the next 30 meters.
So it's kind of like the old layer stripping type of thing.
Yeah. That's a linear problem.
And how big, oh, the loops are 10 to 100 meters.
Yeah, that's just an approximation. So the idea is that your depth of investigation is about the diameter of loop. But that also depends on the strength of your signal and all. But for practical reason, you cannot really do more than 100 meters diameter loop. Or you could, but you would also pick up much more noise. So the usual way to do it is to use this kind of diameter. Yeah.
So what's the smallest scale that turns out to be, you know, really informative as far as the depths that you're looking at?
Are you asking about like resolution, like
Well,
precision?
no, just like if you're trying to get water content.
Yeah.
Are there particular places that, oh, if I had, you know, knew something down to the top 5 meters, that's really useful?
Okay, can you repeat this last sentence, sorry?
Well, you said you're getting depth of resolution that's about the diameter of the loop.
Yeah.
Okay, so what I was wondering about is, like, wouldn't it be nice to be able to take the loop and move it at various angles? So now you're illuminating the Earth from.
Oh, to get other components from your field.
Can you do that?
I think you can do that. Maybe you know, Professor. I don't know if it's Professor, but Mr. Radic, who designed Fuchs 3 SIP device. He works with NMR. He's trying vertical loops settings. But I don't know much about them. But yeah, you can work this towards this direction. Yeah. Then it's a matter of how to set a vertical loop. I don't know how you.
Well, that's why I was asking how deep you need to go, because I mean, you can imagine a loop that's a couple meters. Move that vertically.
Yeah, if you don't want to go very deep, you mean?
Yeah.
Yeah, sure, I guess. But then you wouldn't pick up a lot of signal. Maybe if your loop is too small.
Yeah.
You might not get a lot of water. That's also the main issue, to get the water. This place where I showed the signal, we're actually in the unsaturated portion of the subsurface. It's a karstic environment, so we don't have a lot of water. So we have something that looks like a signal, but we're still like, is it really a signal? We don't know. We're working on it. Thank you.
Which one is yours?
The upper.
The top one?
Yes.
So in here, if you just do the arrows and the
This
keyboard
one?
is easiest. Yeah.
Okay, thank you. So,
Your dreams match.
yeah, I already noticed that. Yeah, so this is only going to take like 5 minutes. It's not so long. So this is my master thesis, which is not ready yet, but this is where we stand. So this study asks, does a snow cover influence ERT measurements? And to answer this question, yeah, we do a model setup and do a synthetic parameter study with it. So yeah, so in one sentence, this study aims to investigate the influence a varying snow cover has on geoelectrical measurements. So here on this picture, you see yeah, measurements with the ERT, and if you measure permafrost, you often have to deal with the snow cover. And at the Schildhorn Massif, there is a permanent model setup with 30 electrodes, which are under the average snow cover of 80 centimeter. So Krautbutter even noticed or said that there could be an influence of the snow cover to the measurements because we're dealing with the electrical measurements, and snow consists of air, ice, and water, so it has an aqueous component, and we know that current reacts to water, and so it could be, the thesis is that the current does not only go into the soil, but both the soil and the snow cover. And so I think, yeah, and so there could be an error source in measuring electrical voltage in that. So this is what, this is the model, and it's quite simple. So there is a snow cover, which is the blue one, and and the green one is the permafrost layer, and there is like an anomaly mass in there, and this is like melted water, and there you can see the electrical resistivities which were given, and yeah, we start with a snow cover of 2.5 meters and 23 electrodes. Yeah, so this is just for the forward modeling. I just wanted to say that the grid is actually quite large. It's from 500 meters to 500 meters because I wanted to minimize the boundary effects. So this is what it actually looks like, the forward grid. And on the right-hand side, you see, yeah, the grid with the electrodes, and yeah. So this is how the inversion would look like if everything is going to be perfect. So I just wanted to say this is the underground, the inverted underground model, how it should look like. And this is what we get if the snow cover is not taken into account in the forward modeling, in the inversion. So we actually don't tell the scheme that there is no snow cover involved. So this is what kind of normally happens. You measure in the field and you get home, and then you kind of invert your data, and you don't take into account that there was a snow cover. So you tell the scheme or the geometric factor that we have a half space. So, and this is what you get. And you have the noise, yeah, there. And if you take the snow cover into account, if you take the scheme and you tell the scheme that there is actually a snow cover involved, and you don't have half space, it looks like this. And on the left side, you see an improvement to the one before on the left side. But on the right-hand side, this is actually the case if the snow cover gets thicker. So this is a snow cover of 3 meters, and this is kind of 1.5 meter. So, and on the right-hand side, you see kind of a mirroring effect, because the electrodes, they just measure one signal, and the electrode cannot know from which direction it comes, so it kind of puts it up and down, you know, in both directions. I thought about this, and what kind of happens is, here. So if you have, this is actually the case, and if you have an anomaly mass, here, not that deep, but very close to the electrodes, right here, you kind of see the same effect that this one has even when you have a very small snow cover. So it doesn't actually, it doesn't only happen when the snow cover is like 3 meters thick, but it happens when the snow cover is 1 meter thick, but the anomaly mass has to be very close to the electrodes so that you can see this effect happening. And then I think this is kind of a nice image here. You see the snow cover thickness down there, and you see a jump there. And this is because I have to say this is the relative change. So what this plot does, it's comparing this left image to this image. So this left image that it does compare, and the right image, and this for every snow cover thickness you see there. So when you got like 2.6 or so, you already see this effect happening. And but this is specific for anomaly mass lying in the depth of 2 meters. And what we are going to do is we want to help the inversion by saying that up there is a snow cover, and please don't mirror this image. So we want to say or want to tell the inversion where is up and where is down, actually. So, but this is not done yet, but this is what I'm aiming for in the future. So I hope that in the end we don't have this high jump there when we do a relative change, but a very more steady line. Yeah, this was just in 5 minutes what my master thesis is about.
So the resistivity that you have for the snow
Cover?
and ice and water, that was, did you say 200 ohm meters? It's
250,000 ohm meters. And I picked these resistivities up from Krautblatter, who did analysis in permafrost, and he wrote in his paper what the typical resistivities of permafrost are. And so I did that, and the conductivity of the snow, I actually, and this is what Andreas asked me before that, because I did a plot, the conductivity of snow and the temperature. And the curve, it looks like this. So this is the conductivity of snow, and this is the temperature. This is 0 degrees, and this is minus 12 degrees. And the curve goes like this, something like this. And you can see here the conductivity does kind of, how do you call it? It goes down because the snow crystals change by minus 2 degrees. And so the current cannot flow doesn't flow that good in a, yeah.
What's the vertical axis on that?
The what?
Sigma?
This is sigma.
Yeah,
This is,
what's the sort of approximate scale do you have?
oh gosh. I don't know.
What are those orders of magnitude? Or
Because I measure always in resistivities because I don't know the conductivities.
then you said that goes down. It's okay.
Yeah. I don't know.
But what would be the change in resistivity that you'd have between -2 and -12?
I can perhaps tell you in electrical resistivity. This is going just wait a second. Okay. So the two how do you call this, extrema. One would be with 25,000, which was like here, I think. Yeah. This is what I actually got there. So, and this was like, it was like, I feel like this. Yeah. So it's kind of
So 60 million or 1.6?
it's 1 0 too much, right?
According to the explanation.
Yeah. Sorry.
So there's,
So probably the other way around.
Yeah.
Because it's sigma.
yeah, that's fine. That's fine. Okay, and then,
Yeah.
see, so that's a factor 4 or this factor 4?
Yeah, 4.
Yeah, but there's a factor of 4 between. Is that right?
It's more than that, six.
Is it 40? Is that 1? So it's 1 times 10 to the 6 and 25 times e to the 4, right? So 0.25. So that factor 4. Okay. So can you go back to that first slide? Something was 250. Is that water? Yes, water?
Yeah. Melted water,
ice.
kind of. So
I
the
also thought that fresh water was really resistive. Is that?
Well, actually, these values are a bit on, I mean, the overall setup a bit kind of mimicking the situation at the Shilton mountain, and that is also one of the motivations, because there is this permanent electrode installation.
Yeah.
They collect data, and we are involved in that, in the processing of that for 15 years now. And so far, I mean, all has been processed and inverted and properly done, but as no cover. There is significant change in there, like up to 3 meters, and with patterns, spatial patterns and stuff. It's totally ignored in the analysis.
Yeah.
Because, okay, snow is high resistive, so how, and this is kind of just was the idea, well, let's look into this, being well aware that, I mean, yeah, it is resistive, and of course it might not make really a difference, but actually these studies show that there is something, and in particular, if you want to do quantitative estimates of the development state, you might actually have to consider it and think about it. So that was, and so the values, you asked about parameter values, they are also like with the 3,000 millimeters, that is actually resistivity that we have at this Shilton mountain, because it's very kind of silty material. It's for a permafrost environment. It's actually a relatively conductive subsurface, and also there is kind of conductive anomalies which would even be then below 1,000. So that's kind of values parameter range is a bit kind of taken from that particular application.
But still, irrespective of the application, if I take ice and melt it, would I not expect a larger?
Oh, no, sure. This kind of is not the right description probably for the melted ice, yeah, for sure. It would be more resistant. So it's kind of, let's say, the row of some anomalies.
Okay.
Okay.
So I guess melted ice is the thing which is misleading.
Yeah.
Oh, nice. Yeah. I didn't, until you had mentioned it yesterday, wasn't anything that you particularly thought of.
Yeah.
But, yeah, absolutely. You put your electrodes there on the surface and
Yeah.
pile it up with stuff, and you kind of forget that you've got part of your material above your electrode.
And the exciting thing is, I think, that you see, you see something happening there.
Yeah.
There is a difference actually. So, and I mean, this is kind of you see the difference in percent here, like 20% difference. It is. I think that matters. Yeah.
Yeah, but are we just opening? Sure.
I think so. Was there anybody else who wanted to present? Did you guys have a presentation? No? Okay. Nobody else? Okay. In that case, then let's do a coffee break, 20 minutes or so. And then we'll show some of the apps and how to get all of that up and running and go a bit into SimPeg, and we can tailor that once we all get back. And
So it's a connectivity when you have to scale that we wish to resolve in geophysics methods, averaging of learning substructures in the preferential pathway. It's kind of really particular at this critical time. It's also being a relatively complex structure. And you don't find that much information on which I could imagine it's although it might be that resistive that all this doesn't matter, but it's one of us, it might matter because the contrast because you have so that was the idea to some simulations in that direction.
Well, it's always interesting, right? This stuff comes out every day.
Yeah. Which papers that are gigabytes are basically showing that if you have this negative response, that basically, I mean, that there is no theoretical explanation for this, so that it cannot occur.
Right.
Kind of with this measurement geometry, so it must be something else.
Yeah, that's a
Is that one like is that like in the 70s? I remember once when I said. Anyway,
yeah,
don't worry.
I can find it.
And that's also I was wondering about because usually depending on with that, possible the setup having more geometry that there might be cases where although a negative EM response, a negative from the EM from the positive is normal EM response, so negative EM response must be something that cannot be EM response, but that actually the peak would also be like latent peaks and have the same polarity as the EM response. So that you have a geometry with an EM measure where you actually get an effect in data which has the same polarity as the normal EM response. And then, of course, it would not be that easy to distinguish it. Should be a geometrical question.
Yeah, I think there is probably that you could be at some location where the polarization field is actually in the same direction as the primary field. I bet you.
Intrinsically, basically, it's always the opposite, right?
Yeah.
Because it's, I mean,
right, but the
polarization is polarized, and the field is gone, and it's in the opposite direction.
But the that's okay. So that's only that's right. So the polarization currents are oppositions, right? So now the question has to be response.
Yeah, like
Okay, so now it's coincident response. That's the only one that holds. If you have coincident response, and there's no way you can get an even reduction. However, the moment that you change, you have to transmit it and replace it and receive something else, and now you can get fields that
Okay.
so that's why recognizing that's
But that would also then perhaps mean that arrangement that there actually the IP response has the opposite. So like with this arrangement, there was basically no negative IP effect possible. So it's always kind of this polarity, always kind of responsive. And the IP is in terms of polarity, always the same as the intrinsic conditions. So it is kind of negative. You have disconnect.
yes.
There's no way kind of to have with this arrangement to get a response to the image. That is the kind of just the other application.
And then the one that Bruce is up is the VR. So now, in that's opposite in direction to. Sometimes it's called okay, so yeah, so that can go in the same. It's opposite. I think it's also possible.
But it helps a lot.
Yeah.
Yeah, I think so.
Kind of we step into the what is going on physically and from that.
Yeah, I know it depends. Sometimes I can hide, sometimes I But I mean, also, how long does it take?
Also das ist schon
Okay, so your first term
Yeah, sometimes it's lots of it makes it fun. And then you take your But you can do something else. Yeah, but also you can go
never use
You can see the
So I'm just trying to that you will everything using adapt code. So the generation code can be enzyme. Just use the same mode ever.
einstelle, ist jetzt vorher in der Vorstellung. Also so viele Regeln.
I want for 10 trades.
Jetzt auszugeben.
To colorize the code code is correct.
Das ist so ein bisschen.
But there are many things that you can investigate and just to show you the students and this is what how we can do it.
Time to
Ja.
results.
Sometimes you have to invest.
I'm not sure whether I can use I will give the results to test the data.
You should check the movement scope if you can do this. So you should know that's
I'm not sure if there is research. Change from the version today, so many
This is It's only better to think about it.
That doesn't sound so urgent.
Don't waste your time.
Also, we can think about what we discussed last week.
How it changes
But I want to
waiting and you have to do a research channel.
So I just wait until your customers
We are so close to the
I was there. It was contract.
Oh man, lots of people.
Lot of people.
Yeah, but if I want to find some near it's too fancy for me. Really good at hard to see so many people in Germany.
Yeah.
That many from lots of activities around the Europe.
No, I think I mean a lot of turnout. It is a bigger one.
Also Chinese. Yeah, it's very familiar with that. China.
Yeah, but like the Japanese games were quite famous. You also Japanese games. Oh yes, here is. Yeah, thanks. Yeah. What? No, it's okay. Now I'm doing the revision. Yeah, but it's over there. Yeah. This won't be uploaded right now. This is just sitting locally. So yeah, yeah, that'll be fine.
Thank you.
We can.
There's a couple people still. I think there's a couple people still out, so we'll give them a couple minutes. But my screen is currently looking at this, right? Can you tell?
Really?
Okay. No worries, there's nothing you need to do. It's fine.
It's pointing.
It's just capturing this. It's not capturing that part. Yeah, so what I'd like to show you is a few of the resources that we've been developing. I'll also go through how to get up and running with the apps, and then how, if you're interested, to extend and contribute to those as well. So there's the apps, and then there's also, we've got some notebooks that show how to use SimPeg, which is the simulation software that we've been developing as a group. So I told you a little bit about the GPG already, a little bit about EM. I'll briefly show you SimPeg, and then we'll jump back to the apps. So SimPeg is an open source project that we've been working on at UBC, and the goal is to bring all of the geophysical methods into one place. So to be able to simulate and invert any type of geophysical data all in the same framework. And so we share a lot of motivations with like the PyGimli project, and I've had a great chat with Florian, and we're looking at There's a few potential areas of collaboration and overlap. There's a lot of things that are different in the way that we think about things. So there's sort of a couple different modes of interacting and doing geophysics in the open and with Python. And so this is our take on it. And so this is the SimPeg website right now. There's a few resources you can get to. So there's a paper that describes SimPeg. There's a recent one that came out on the electromagnetics side of things. Both of them are in computers and geosciences. There's the documentation. So within the documentation, where I would actually recommend you start is with the examples. So there's all the installation and all that sort of stuff, but really the first thing to do is actually see what can be done. So there's a few examples that we have that are in publications. Can you guys see that okay from the back? That's okay. So there's a few examples that we have that are scripts that'll reproduce paper, figures from publications, so you can look at those if you're curious to see them. Some of them are a little more involved just because the plotting code is like, we wanted to make them, publication quality, so the plotting code is a little more intimidating. So those aren't necessarily the place to start. We've got a few that show just a basic linear inversion. So one, like a typical Tikhonov style inversion, one that we demonstrate a couple different norms that are plugged in. So if you want to do like a compact norm in your inversion, this will show that example. There's some that show generating meshes. So things like tensor meshes, octree or quadtree meshes in 2D, as well as curvilinear meshes, and then how to do some basic plotting on them. One thing that we have in SimPeg is called mappings. And so what this does is this lets you translate from, if you want to invert, say, in log conductivity space, then we need to map that to true electrical conductivity to actually run the simulation. Same thing if you want to do like parametric models or things like that. That's all implemented as maps. And then we get into the different methods that are in SimPeg. So right now we've got gravity, magnetics, there's DC resistivity, frequency domain EM, there's natural source EM, time domain, there's some fluid flow with Richard's equation, and some very basic straight ray seismic tomography. So that's sort of what I would say is more mature in SimPeg. There's some development with spectral IP, as well, but that's more off on a development branch. So if that's something you're interested in working on and collaborating with us, you can get in touch. And on that note, we have a Google forum. So if you get to the docs, or it should be on the main page of our website as well, there's this Google group. So that is a good way to get in touch with people who are using SimPeg and developing SimPeg. It's just like basically an area where you can ask questions. And so that's sort of the best way to go. Because emails works not too bad, but this way at least, a handful of people will see it. And so hopefully somebody will get back to you. Cool. So I'm just going to go back then to GeoSci. And let's jump over to EM, and we'll take a look at some of the apps and then some examples that show how to use SimPeg. And please do stop me if you've got any questions or thoughts or comments you'd like to raise. So we saw this earlier. This is EM GeoSci. This is the open source resource we've been working on on electromagnetics, primarily for this course. There are some areas that are under construction. So you will come across some pages that say under construction. So be aware of that. That's also a great place to contribute. If you have some ideas of what should be on those types of pages, all you have to do to edit content or contribute content is go through GitHub here. So each of these pages are linked. And then we get an alert that says somebody fixed a typo, and then we bring it in. So we had a quick look at the case histories. I'll show you that in a little more detail here. So this is the current collection of case histories that we have. They're not really sorted in any particular order right now. But if you are looking for an example in mineral exploration, for example, or in oil and gas, we do have some keywords that'll help you find these. And each of them are arranged in that same 7-step framework that we talked about yesterday. So we've got, if we look at, for instance, at Mount Isa, we start with the setup, go through properties, survey, data, processing, interpretation, synthesis. And then we have an extra section for lessons worth highlighting. Because sometimes, there are some just like key learnings or rabbit holes you went down that were interesting. And we do want to have a place to capture that. So if you are interested in contributing a case history, the best way to do that is to get in touch with us first, and then we'll help iterate on a Google Doc with you, and then we'll get the first instance live on the web, and then you can edit that from there. So we're hoping to streamline that a little more at some point, but right now, contacting us is the best way to go. Okay, so then the apps. So we have 2 styles of apps that have been developed. There are the EM apps, and that's what we demonstrated yesterday. And these are really basically sort of GUI style interactions for running numeric simulations. So you won't really see much code. It's basically a small notebook that's designed to launch some slide bars and enter boxes with plots of numerical simulations. The other style that we have are these simulation notebooks. And these are much more, if you are interested in actually building up your own numerical simulation, you've got a specific geologic setting, you want to build that up, you know what your survey parameters are. These expose all of the code. So we go through step by step how to build a mesh, how to put your model on the mesh, defining the survey, and going from there. So I'll show you one of those as well afterwards. So let's start with the EM apps. So the way that we recommend that you get started with these is through Microsoft Azure. So Microsoft has a cloud service that they let us run these for free, basically. And so if we go here, you can see what's in the library. But right now, you'll notice that this little run button is grayed out. So right now, that means I'm not signed in. And so you need to first sign in and make a copy of these notebooks. So what we can do is just sign in. If you don't have an account, it's free to create. So you would just, when you go to the sign in, there's also a button that says sign up. So you would just do that. And then this is like our hosted library. And so in order for you to get a copy, you're going to actually clone it. And this will be your own copy that will persist. So if you want to make changes or make notes or things like that, this is your own copy. So we will clone that. And since Doug already has a copy of this, that's why it's suggesting like, hey, do you want to overwrite it or not? I'll just overwrite it in this case. And then we get to the apps that we demonstrated yesterday. And so there's, I believe, 26 notebooks at this stage. So going through, starting with DC, then we have some frequency domain examples. There's a marine CSEM example, MT, and then time domain EM. So to go ahead and run any one of these, we just click on it, can get it started up and running. So let's take a look at this guy here. So this is one example that you can look at the shielding example with. So we've got a cylinder, and there is a layer above that, and we're going to run a DC resistivity experiment. So sorry, I may have done that quickly. All I did is just click on it to launch it, and then it created a notebook server for us. So then what you want to do to actually run it, so there's 2 ways to run it. You can either go cell by cell. So each of these is a cell. So if I click on it and then do Shift Enter, that will run it. And so what it's doing right now is just installing all of the dependencies. So here, this EM examples repository, that's a code base that we created that actually build up all of these plots and build up the little interactions. So it's just installing that. And well, from there we can go ahead and import them. So that's going to take a second because I think it's still, there we go. So you know it's done when it has a number here, or when this guy is open, an open hole versus a closed hole. Okay, so in this case, we get this app that's been pulled up. So we have all of our widget interactions, and then there's a couple plots below. So in this case, we can build up a model. So we've got 3 units. So if we look at our just sketch of the problem here, we've got a background resistivity, we've got a layer, and then we've got this cylinder beneath. So what would you like to see for a model? So we've got a background. What should the background be? Anybody? Perfect. Okay, and then do we want a resistive or a conductive layer? It's okay like this? Okay, so we've got a resistive layer, and then we'll make let's make a conductive target beneath. So 100. So this is our model that we built up. And then perhaps the first thing that we want to look at are the currents. So in this case, you can see, oh, that's linear scale. So if we look on log scale, it's a little easier to see what's going on. We don't have, we don't have much necessarily going through this layer. Most is up here still, but it's not necessarily, it's not as, sorry. It's not quite as dramatic because it's not up as high. Okay, and then from there we can look at charges. So as we saw yesterday, most of our charges we got right at the electrodes. And then if you want to go ahead and look at the secondary charges, we'll see that we really get most of our buildup now on the layer. So the thing that we're really looking at in this survey when we have such a resistive layer in there is the layer. We're hardly getting anything building up on this sphere. And from that, we can look at our total potentials, total or secondary. So total, we see we're looking mostly at our electrode locations. And then secondary, so we've just removed the background. We're really, again, looking just at this resistive layer. So there's a few other notebooks that you can flip through, and quite a number of the figures and the images that were in the slides yesterday were created using these apps.
So the codes that actually read the images, that's not accessible in the...
So that's the code that's building the images is this EM examples library.
Okay.
And so it is, it's on GitHub. So you can, you can look at it there. And then basically if you want to see any given app, it's just looking at sort of this import statement right here. I don't know if you can see that, okay. Will tell you this is the file to look at, and then this is the code that's going to build that app. Yeah, it's coded in here. Yeah, and so a lot of this code is still cleaned up. Some of it is been sprinted to create an app. So that's sort of where that is. If you really do want to demonstrate the forward modeling aspect of things, that's the simulation notebooks. That's where to look. Okay. So I'll show you that now, actually. So if we go back to, let's go to EM GeoSci. And then if we go to our apps, so these simulation notebooks, these are going to expose all of the code step by step. And they're also up on Azure. So there's less of these, just because they are a little more involved. But we can, again, go ahead and clone this. So there's a few examples that we have here. Two of the ones that we would have seen yesterday are the frequency domain vertical magnetic dipole sounding over a sphere. There's also one in the time domain, just on the next page here. So those two are there. And then there's a series of these MT tutorials. So in this, what we do is actually, we've written a leading edge article, and we walk through step by step how to actually construct like a finite difference solution for the 1D MT equation. How do you build a mesh? And then how to actually go about and solve the inverse problem. And then examine a few things like regularization parameters and see what kind of impact that makes. I'll flip through them briefly just so you get a feel for what they are.
Question. Go offline.
So if you go offline, you'll need to actually download these. And then there's like the instructions actually for installing are already embedded in the notebook. We do have some instructions, I believe, on EM GeoSci on how to actually download and set things up yourself. Are you familiar with Python? A bit? Okay. Yeah. So the best way to actually like get up and running, I don't know if we have that in here. Be building that in, is to install Anaconda through Python. So I would actually follow, if you're going to go through the installation yourself, I would follow the instructions on the Simpeg website. So on the Simpeg docs, there's a getting started. And this will tell you how to install Python and how to install Simpeg and all of that. Because those are the main dependencies that you'll need for running any of these. So with the MT tutorial, we start out here setting up and solving the 1D MT equations. So I'm not going to go through this step by step, but I'll just kind of give you a quick overview of what's here. And then if there's pieces that you guys are interested in jumping into a bit, we certainly can. So here we're going to install Simpeg, which is the dependency, and then bring in some standard packages within Python, within the scientific Python stack. And then we walk through how to discretize Maxwell's equations for the MT problem, where things are living, so on faces, cell centers, or edges, what the discrete matrix system actually looks like, some things you want to consider when designing a mesh. So what is your smallest skin depth? What is your largest skin depth? We show you how to set that up and plot it. And then assign physical properties to that model. And then here we're going to go through and assemble the A matrix. So in this case, all we do is build up each of the block matrices and then just assemble it all in our large A matrix. And then you go ahead and solve. And then, of course, it's generally easier, instead of looking at electric and magnetic fields, we want to look at impedances. So we can do that and then convert it to apparent resistivity and phases. And then all we do here is then basically show how to take essentially a script and then turn that into a function so that it can be reused. And then this function here is reused in the next set of notebooks. So that's basically that one. The next one that we go through is now going to sort of assume that you've done your job discretizing the MT equations. And we're going to actually look at two things. So one is mesh design. So that's getting back to skin depths and asking questions of, if I make my cell sizes, my smallest cell sizes, if they're too big, what does that actually do to my simulated data? And if I don't extend my boundary far enough, again, what does that do? So there's a little, I'll run some of these so that we can have a look. So it's again going to walk through the setup of just how to actually build up a model, define some frequencies. And then here we actually walk through, okay, we're going to use a tensor mesh. So that means that the cells expand. So here we're basically just building up what should that padding look like? How do we make sure that we've gone far enough? So we figure out our deepest skin depth and then basically say, let's go well beyond that. Okay. Actually, I'm not going to. So here, this is an example where we've set up a 3-layer model and we compare with an analytic. So we show a few examples of how to actually test code. This is like one set of testing. There's another notebook that goes into detail on how to test sensitivities as well, if that's something you're interested in. But that's a little detailed for this notebook. And then here we also demonstrate really the classic example of non-uniqueness for MT, which is non-uniqueness with the conductivity thickness product of a thin layer. So if you simulate 5 different models, each having the same conductance of this unit that's our target unit, we really do see that within any sort of reasonable noise level, it's very difficult to tell the difference between any of these things. So it's sort of setting the stage for asking questions about what can we actually expect from the inversion before we get there. And there's a little widget to add noise.
Yeah, to run a set of instruction like in 69 below, you just type enter or?
Yeah, just shift enter. Yeah. So by getting through the second notebook, we've hopefully explored a few things of like, what can you expect from your data? How do you know that you've set up a proper mesh? And then this one, we go through and look at the inversion. So there are a few parameters that we examine. So we set up the inverse problem like a typical data misfit plus a regularization term. And then some of the things that you can explore in this notebook are what should you choose for beta? What internally does your phi m look like? Like how small or how smooth are we going to make this regularization? And what impact does that have on your results? And then we also look at different stopping criteria. So overfitting versus underfitting your data. So in this case, we use a 5-layer model. Go through, simulate some data. We walk through in this notebook a lot of the pieces of SimPeg and how we're thinking about the inverse problem. So this is a nice way to get exposed to the style of thinking that we use in that setting. And then we go through and demonstrate performing an inversion, looking at Tikhonov curves. And then here, there's a couple plots that now show, when we've hit our target misfit, what kind of model recovery do we get? And then you can go in and play with all of the different inversion parameters and explore that for a fairly simple model in basically real time, because it is a 1D inversion. So I know that's a very quick overview. Are there pieces that people would like to dive into a little bit, or questions that this prompts? Not so much. The associated article with this is in the leading edge. We can send around with the email that we'll send out later on. We'll send around a link to that article as well, so that you can see what accompanies this.
You get the linear type of inversion, like
general single variable composition and the pseudo inverse? Or what type do you?
Here we're using all a gradient-based inversion, and because this is the MT, it's a nonlinear.
Okay.
It's a nonlinear inversion.
I don't know if I didn't see other problems like other.
Yeah, so we don't have, in this set of notebooks, this is really electromagnetics focused. Yeah, but there are examples in the SIMPEG docs. Yeah, yeah. And if there isn't something that you're looking for, just ping on the Google form, because there's a lot of examples that we have internally kicking around that just haven't made it to the web yet, so.
The other thing is we have a whole host of plan apps and examples with respect to inversion and physical techniques, but it just takes time to put them all together. Yeah. The reason this one was done is that as we were going around the world, it was interesting how many people in different places were interested in MT. It was also quite interesting that there were so many people out there that had access to a 3D inversion code, and they were taking their data and just plonking it into this code, pressing a button and getting something out and believing what they had. And if you talk to them, they know they know all the words. Okay, regularization function, Tikhonov curve, trade-off curve, data misfit. At a conversational level, it seems like a good go. And then you start probing a little bit, and it's like, wait a minute, there's no basis.
Yeah.
So that was what prompted the development of this particular notebook. But this is a non-linear problem. There's a whole host of things that one could do just at the linear problem stage. And it's used for really good teaching.
Yeah, I'm giving my first class in person. That's why.
Oh, good. So you can develop. You've got a couple of days to develop that. And
Right.
We'll critique it for you. That's good.
Yeah.
Your thoughts.
Exactly. So the other one that I'll show just briefly, so you can see a bit more of the setup for just a forward simulation. This is doing the time domain sounding over a sphere. And so here what we've done is we've got a sphere, we've got our transmitter above it. So this is a cylindrically symmetric problem, which is kind of nice because then we can use the cylindrical mesh, which is very fast. And this is, again, all using SIMPEG focused on the electromagnetic side of things. So we bring in our packages. The time domain package is within the electromagnetics portion of SIMPEG. And then we'll bring in some solvers as well as utils and things like that. If you're not familiar with Python, these are standard packages. So NumPy is like effectively MATLAB. It does all your matrix operations. Matplotlib does all the plotting. And then SciPy, they've got a whole suite of things. We use a lot of their sparse matrix linear algebra. But here they also have constants that are stored. So we'll use that as well. And then in this case, all we're going to do is set up, there's 3 parameters. We've got our half space conductivity, our sphere conductivity, and our air. And then we'll figure out where the sphere should be. We set our survey parameters. So we're going to bring our transmitter 20 meters above the surface and have our receiver offset by 8 meters. And we'll do 30 time steps. And then again, thinking about mesh design in this case, because we're in the time domain, we're going to look at diffusion distances to help us figure out what should the smallest cells be and what should the largest cells be. And then we walk through, where do things live? So cell centers, faces, edges, etc. So all this is doing is just setting those mesh parameters. And then we define a mesh object. So what that actually means is now that we have our mesh, this actually stores all the geometry. And it is, like Python is an object-oriented language. So what that means is once I create a mesh, it actually has properties and methods. So we can look at, for example, the number of cells on our mesh. Or we can also then access things like all of our differential operators. So we have the edge curl, for example, or the face divergence, because those are all defined based on your geometry. So one of the things that's helpful to do instead of, printing all of these variables is it's useful just to be able to look at your mesh and say, okay, I know it should go at least this far. Is it going that far in all my dimensions? Yes. And so you can get a handle on then, like, what does it look like for what I'm simulating? So now that we have a mesh and we've defined those parameters, defining our model, we can put our model in our mesh. And then we'll go ahead and plot that and do a bit of a sanity check is this what we expected? So we've got our air above, which is 10 to the negative 8. We have a sphere, it's a conductive sphere, and a moderately resistive background. And then here, what we're going to look at for data are dB dt. We'll do the vertical component. So we create our receivers. And then we'll use a magnetic dipole source. That's located, at the location we defined before, and it's oriented in the Z direction. And here we'll just use a simple step-off waveform. So that gives us all of our model and our survey parameters. So we can then go ahead and actually set up the rest of the forward simulation. And here, we often do things like this, is just printing out a few facts about what you've just set up to again, sort of sanity check that all is what you expected. So then here we're going to actually solve for the fields, because it is useful, like with a lot of the images that we generated yesterday, we want to look at the currents and the magnetic fields everywhere in our domain. So we'll go ahead and solve with the sphere, and we'll solve without the sphere so we can do a comparison. And then here, this IPyWidgets library, that's the one that we've been using to actually build up all of the slide bars and text boxes and all the buttons and things like that. They make it very easy to just write a function and then say, please make it interactive. So in this case, we've got our dipole source over a sphere, and we can actually step through in time and see what's happening. So I've got the time in the title, so you can watch as we slide through. So almost immediately, we see we've got currents isolated up here. And we can watch as we go later and later in time. You notice the color bar is changing as well. So we're losing amplitude through time. And so once you get a handle on, what are the magnetic fields actually doing, in this case, we can then go ahead and actually look at what are our data? What should our data be looking like? So here we're going to look both at the predicted data and then the background and see, the classic sensitivity question is, can we see the sphere? Is there some difference in the data between the sphere and just the background? And so in this case, when we look through time, there absolutely is. Yeah. Are there any other? I hope this has given you a bit of a sample of things here. I know it's quick, but I know it's also 20 past 4 on the second day. So. Okay.
Different from Fortran.
Yes, very different from Fortran. Yeah, so in terms of ways to get in touch, I'll just show you that again, because I think that, for getting started, as soon as you can look at the docs, but it's very helpful to contact a real person. So again, this is where you find the forum, and I'm on there. There's a few other people who keep on top of that. So. No worries.
I want to make one comment about case histories. And that is that as we're, there's just so many case histories around that are out there. And what we've been trying to do is to find things that have kind of a unique application and something that's got really high impact. So that, it's an area that's it's a mineral exploration, it's a water top and something like that. It's the use of a particular type of survey to answer a question with electromagnetics that is kind of like a no-brainer. Somebody who's not in the field kind of picks this up and looks like, well, here's the problem, here's what they did, here's the process of interpretation, this is the output, like, wow, this stuff really works. Anything that's kind of really challenging and examples that, kind of need an expert to figure out whether you're making any progress or not, doesn't really help our situation. But the one thing I might ask is, as people are looking through, the case histories and seeing the various applications, if there's something that really resonates with, like a really special case history, kind of like the one we did this morning, I thought it was really good on the landfill. I mean, that's a quality case history. It's quite clear what some of the conclusions are. Those are the things that we'd like to capture and put on the website. And the way that we do it, we have a template that tries to make it logistically easy for you. So it's basically a Google Doc form that you just cut and paste things in. We'd like to have it that the material is already publishable, because then we can have a link to the paper so somebody can read the big paper. And then from the point of view of the case history on the website, it's just sort of a pricey, something that's like a 5 or 10 minute read. You can kind of get through it and really get the overall essence of that stuff. Then from that, there can be links to the paper, which is, but overall, then the idea is that we amass a number of case histories, different applications, different parts of the world, different kinds of surveys, all of which show the success of EM when it's been properly. So you can just kind of think about that, especially sort of going to different conferences and just your own background. Okay, that was a really great example.
EM includes ERT.
Yeah, absolutely.
But you're looking for case histories that are useful in real life, right?
Yeah.
I don't know. I'm just. I did throw away 8% of what I did.
Our Belgian colleagues are doing it. Get a lot of fun. Anyway, that's a request. Wow, the energy level is really high.
Fair enough. Well, I think with that, we'll wrap up.
I think so.
Yeah, thanks to everyone who presented today. That's been a great chance for us to get a perspective on what people are working on, and we'll capture that in the blog and we'll send that to you. And you're absolutely free to edit the words on your write-up and add things, suggest things, and we'll update that to your liking.
To be able to view yourself on the blog. There you go. But it only lasts forever. It's a good thing about digital internet, right? As long as there's enough server background, it's just going to be there forever. Anyway, I just want to thank everybody. That was great. We really appreciated the opportunity to be here. And yeah, this was a high quality meeting as far as the people who are here and their active interest in EM. And yeah, we're really pleased to have had the opportunity to come to Bonn.
Yeah.
So thank you.
Thank you. We were glad that you were here. So for sure. And actually, for me, the second day was, I mean, like you said, I mean, it's kind of a different thing. But I learned a lot again today. And I also got my homework with all these new tools. So yeah, it's been really, really excellent. And yes, thanks again for stuff on your world tour.
On our world tour to eat more, right? So we see at lunch today we thought that Germany was the place to have schnitzel, and it is. But then we found that the best schnitzel is in Austria. That's where we're going next. So.
Perfect.
Okay, thanks.